Hello, welcome to another module in this massive open online course where we are looking at the linear classifier, and we have seen how the support vector machine for linear classification of two sets of points can be formulated as a convex optimization problem. Okay. So, in this module let us continue our discussion. Let us make this paradigm a little bit more sophisticated by incorporating also a certain amount of classification error for approximate classification. All right. So, what we want to do is I want to explore the possibility of approximately classifying two sets of points. Okay. And the reason for that I am going to explain it shortly. So, we have looked at so called hard or exact classification. So, let us now also look at building an approximate classifier, and approximate classifier in the sense that there is some possibility for a classification. So, can incorporate. So, you can say this has with some classification error. So, this allows for some classification error, and the reason for that is as follows. Now, so far what we have seen is basically the following. We have two sets of points, okay, and we are trying to separate them. So, this set corresponds to hypothesis H0, corresponds to hypothesis H1, and we said we can separate them using a hyperplane. But if you separate them simply using a hyperplane, that results in the trivial solution. So, what we said was we are going to fit a slab, the thickest possible slab. So, we are going to fit a slab and maximize the separation, or maximize the, we are going to use two hyperplanes and we are going to maximize the separation between the parallel separating hyperplanes. Now, the problem with this is the following thing. Now, what we have said is the following thing. We have said the optimization problem for this can be formulated as follows. I want to minimize, remember we said the distance of separation is 2 over norm A bar. So, if you want to maximize the distance, we have to minimize norm A bar subject to the constraints A bar transpose x bar I plus B greater than or equal to -1, and A bar and this is for I equal to, that is the first set of points, I equals 1 2 up to m, and then we want to have A bar transpose x bar I plus B less than or equal to -1 for I equals m plus 1 up to m plus n, and this is your convex optimization problem for the linear SVM. Okay. This is what we have seen. This is the for the linear. Now, the problem arises if, what if the sets of points are not linearly separable. So, what if, what happens are not what if they are not linearly separable? For instance, you have a situation where you have some points belonging to hypothesis H0, and at the same time you have some points belonging to hypothesis H. So, these are the H0 points and these are the H1 points, and you can see there are two clusters, but if you try to separate them by any plane, alright, if you try to separate them by any plane, okay, you are going to have some classification error. So, if this is the hyperplane, so you are going to have, for instance, this point here, which are H1 points classified as H0, and this point here, this point here. So, these are the misclassified points. So, these are your misclassified points, and these can also arise due to the following. These can also, and this is a very important point, this can also arise due to noisy data. So, what happens is, normally these two clusters, that is belonging to the primary user absent and primary user present, are well separated, but sometimes because there is noise in the system, and that is reality. In practice, frequently you have no observations are noiseless, all the observations are noisy, which means some of the H0 observations are closely clustered with H1 and some of the H1 observations are closely clustered or closer to H0. So, there's in general there's an area where there's a kind of gray area where there's a mixing of the points corresponding to these two data sets. So, in the sense that these two sets might not be linearly separable, that it's not possible to find a plane, or it's not possible to fit a nice slab between them, so that both these sets of points lie on different sides of the slab, which means one has to tolerate, so they are not linearly separable, so one has to tolerate certain amount of classification error, that is the point. So, since they are not linearly separable, this implies one has to tolerate some percentage of tolerate some percent of classification error, alright, which means basically there is not exact classification or hard classification, which implies that our classifier is only going to be an approximate. So, it is only going to be an approximate classifier, but we want a good approximation, okay. So, as far as approximations go, if you want to have an approximate classifier, then one can draw any hyperplane, alright. For instance, one can draw a hyperplane that looks like this, okay, but you can see, or you can draw a hyperplane that looks like this, but you can see, although that is an approximate classifier, that is a bad approximation, because it's roughly, I mean, the data sets are not well separated, alright. So, we want to design an approximate classifier, but at the same time an approximate classifier that minimizes the, you can say that minimizes the number of misclassified points, or minimizes the classification error, or that is very accurate, alright, to a very high degree, okay. So, that is what we say, we want to design an approximate classifier, but a decent approximate classifier that gives you the best classification that is possible, or that minimizes the classification error. That can be a good metric. So, minimize the classification error. Minimize the classification error, okay. Now, how do we do this? We can do this as follows. So, here remember, consider the points I equal to 1, 2 up to m, we have the condition A bar transpose x bar I greater than equal to 1, or A bar transpose x bar I plus b greater than equal to 1. Remember, this is for perfect classification. Let us say no, this is for a perfect classifier, if perfect classification is possible. On the other hand, when this is not possible, what we will do is we will modify this as follows: A bar transpose x bar I plus b greater than equal to not 1, but 1 minus u I, where this u I, remember we are still talking about I equals 1, 2 up to m, where this u I is termed as a slack. So, you allow for a certain slack in the constraint, that is, the constraint need not be exactly satisfied, that is A bar transpose x bar I plus b is not greater than equal to 1, but for some points, for some I, it can happen such that it is greater than equal to 1 minus u I, where u I is some kind of slack that you are allowing in this constraint, alright. So, this u I has to be naturally greater than equal to 0, because if u I is less than or equal to 0, then A bar transpose x bar I plus b is greater than or equal to 1 minus u I, which is greater than or equal to something that is greater than 1, alright. So, that is not necessary, okay. As long as it is greater than or equal to 1 or something that is slightly less than 1, that is also sufficient. Now, you can see this allows for some classification error, because consider two cases. One is if u I is less than or equal to 1, then this implies 1 minus u I is greater than or equal to 0. This implies A bar transpose x bar I plus b greater than or equal to 1 minus u I greater than or equal to 0, which means it still lies on the other side of the hyperplane, okay. Still lies on one side of hyperplane, okay, that is A bar transpose x bar I greater than or equal to 0. However, if u I is greater than 1, this implies 1 minus u I is less than 0, and this implies A bar transpose x bar I plus b, which is greater than or equal to 1 minus u I, but this quantity 1 minus u I is less than 0, which implies that A bar transpose x bar I plus b is less than 0, or which implies that this constraint can be less than 0, which implies that this point can be misclassified. This particular x bar I can be misclassified. So, in that sense, this is only approximate. So, in that sense is only approximate classification, in the sense that you are allowing some of the points, you are allowing a slack in these constraints, or basically you are allowing some of the points to be misclassified, in the sense that some of the points can have a slack that is large enough, so that they cross over from one side of this hyperplane to the other side. So, some of the hypothesis 0 points can be classified as hypothesis 1 point. So, you are allowing a certain slack, or you are allowing the possibility for classification error. Now, similarly, when you look at I equals, similarly for I equals up to m plus 1 up to m plus n, then what happens? Remember, for perfect classification we have A bar transpose x bar I plus b less than equal to minus 1. This is for your perfect classification. This is when your classifier this is for a perfect classifier, that is no classification error, implies that there is no classification error. However, there is classification error when there is when you want to allow the possibility of points being misclassified, again due to noisy data, when linear perfect separation is not possible, then you can again allow some slack a bar transpose x bar I plus b is less than or equal to -1 plus ui. Okay, remember we are still talking about I equals m plus 1 up to m plus n, where ui greater than or equal to 0. Okay, so ui is greater than or equal to 0. So, if ui less than equal to 1, again it still lies on the other side of the hyperplane. If ui is greater than 1, then you have a problem, in the sense it crosses over. So, if ui greater than 1, this implies there is a classification error. So, by introducing the slack in these constraints, you are allowing the possibility that you are recognizing the possibility that the data is indeed noisy, and you are allowing for some slack in this constraint, that is the possibility, allowing the possibility for a few of the points to be misclassified. So, therefore, now the optimization problem can be formulated as, now remember we have so far not talked about the objective. Remember, we want to build an approximate classifier, but you want to build the best approximate classifier. Now, what is the best part of it, that we will come to shortly. So, but we have the constraints. What are the constraints now? The constraints now, a bar transpose x bar I. So, we have the constraints a bar transpose x bar I plus b greater than or equal to 1, which was there previously, now greater than or equal to 1 minus ui greater than or equal to 0, I equals 1 to up to m. Okay, so, now you have these new constraints on ui, all the ui's are non-negative. Similarly, for the other set of x bar I, a bar transpose x bar I plus b less than or equal to minus 1, I equal to m plus 1 up to m plus n, or and previously was less than or equal to minus 1, now less than or equal to minus 1 plus ui, again ui greater than or equal to 0. Okay. And now, in fact, if you write this as a vector u bar, you can write this as a comprehensive constraint u bar equals u1 u2 up to u m plus n. You can combine all these things and say u bar greater than or equal to 0. This is a component wise inequality, all right. Each component of u bar must be greater than or equal to 0. So, this is your component wise inequality, and here you can simply minimize the total slack. Now, what is the best approximate classifier? The best approximate classifier is basically the one which minimizes the total slack. That is, remember, we are doing this slack because we are helpless, right. But at the same time, we do not want to allow too much of slack or too much of tolerance. We want to keep the tolerance to as low as possible, which means we have to minimize the slack, or in other words, we can minimize the total slack. Okay. So, I can minimize the total slack summation I equals 1 to m plus n u I, which I can write as 1 bar transpose u bar, where 1 bar is simply the m plus 1 vector of, this is the m plus 1 vector of all ones. Okay. So, that is your objective function, minimum 1 bar transpose u bar. Let me write this again clearly, minimize summation I equal to 1 to m plus n u I, which is nothing but the summation of all components of the vector u bar, which can be written as minimize 1 bar transpose u bar. Alright, remember each component of u bar, each ui is non-negative, that is u bar component wise greater than or equal to 0. Okay, so that is basically this is basically your approximate classifier, or you can also think as the soft margin classifier and so on. So basically this is approximate or this can also be, if the previous one is a hard classifier, this can also be known as a soft classifier, in the sense that it is soft, that is not it is not a hard partition between these things, it is a soft one, it is a porous one through which some points can pass through, alright, but it is not the same thing as having no partition at all, which is basically where all points are on either way. So, you try to build the best approximate classifier. And now you can extend this to a regularized, or so you can regularize this. Previously we wanted to fit the thickest slab. So there are two objective functions, a bar and one that minimizes the slack. You can consider a combination of them. So norm a bar plus lambda times 1 bar transpose u. You are aware of this lambda, similar to many optimization problems, this is the regularization parameter. Constraints are the same, subject to a bar transpose x bar I plus b greater than or equal to 1 minus ui for I equals 1 2 up to m, a bar transpose x bar I plus b less than or equal to 1 minus ui for I equals m plus 1 up to m plus n, and u bar component wise is component wise greater than or equal to 0. Remember u bar, this is the slack vector, each component of that represents the slack. Now, if linear classification is possible, then naturally these components of the vector u bar will either be 0 or close to 0, alright, similar to what we have seen before. But of course, if linear classification is not possible, then several of these u's will be greater than 0. In fact, some of these might even be greater than or equal to 1, which shows that basically some of the points are misclassified. However, we want these elements to be as few of them to be greater than or equal to 0 as possible, that is, you want the slacks in general to be as low as possible, as close to 0 as possible. That is why we are minimizing the total slack. In fact, in this case we are minimizing a weighted combination of the distance between the separating hyperplanes plus the slack. So that fits the thickest slab while allowing certain amount of misclassification, alright, and you are minimizing a linear combination of these two objective functions, alright. So this is basically the regularized minimization, or you can think of this as a regularized classifier, alright. So we will stop here and continue in the subsequent modules. Thank you very much.